Hey guys, so we have had quite a few discussions now on random walks. We saw that there are these nice properties of random walks, namely that average distance squared as a function of time will go linearly, and so we derived the exact result for the discrete random walk in 1D. Then we saw how there is a connection between these random walks which are discrete in nature, and then when you make it continuous, time and space, you get you get the diffusion equation. So, and in that context I had mentioned that in fact this result, that the average distance covered as a function of time will go as a square root of the time, and the fact that this holds regardless of whether you make the time and space discrete or continuous, or you keep one of them discrete and make the other one continuous. It doesn't matter. In all these contexts you get this basic rule, which is that distance typically goes as square root of the time. And so this result is very general, and this is called diffusive motion. And so today in this module I want to motivate where this comes from. What is the cause for this kind of generality, and why do random walks appear in all kinds of contexts where apparently there's nothing to do with a drunkard or a random walker involved. There's no obvious way to see this, and yet these results are so generic in nature, and they appear in whenever there is stochastic variables involved, they appear. And so I want to show you how this is connected to a very deep and important theorem called the central limit theorem, right? Probabilists spend a lot of time going into the rigorous formulation of this theorem and proving it, and analyzing various technical aspects of it. But our goal here will be to simply motivate and in fact just state the theorem in a very non-rigorous way, and then do a few checks. In the true spirit of this course, we will do some numerical checks to explore the generality of this theorem, and then set it up in such a way that it will actually it makes it amenable to more such explorations, which I will allow you to potter around and play with. Okay, so here is my non-rigorous statement of the central limit theorem. Suppose you have n random variables, right, and x1, x2, so on till xn, and they all have different means, mu1, mu2, so on, mun, and standard deviations, right, sigma 1, sigma 2, sigma 3, all the way up to sigma n. Now it's often of interest to consider the sum of all these random variables. So a lot of different contexts give us sums of a large number of random variables, and that's where the central limit theorem comes into play. Whenever you have a sum of a large number of random variables, regardless of the microscopic information or the precise form of the distribution of each of these random variables, it turns out that the sum of all these random variables tends to go to a definite distribution, and that is the Gaussian distribution, whose mean is just simply given by the sum of the means of all these different random variables, and whose variance sigma squared is simply the sum of the variances of all these random variables. So that's why Gaussians and these bell-shaped curves are so ubiquitous. You might have encountered these in the context of your marks distributions, for example, in your among various different students, or if you were to study the distribution of heights of various members of some group in your own class or somewhere in some other sample, you would find a bell-shaped curve. Or you might have encountered bell-shaped curves in the context of your lab experimental results that you measured of some data set, and then if you just made a distribution, the histogram is likely to be like a bell curve, right? So there is some underlying sum involved. That's the type of that's the implication, all right, which I'm trying to get across. Now, so let's do a few exercises to see whether this is a reasonable thing. So what have we done in the past? We have said that your random walker can either go to the right or left with some probability p, and 1 minus p equal to q, and we have checked this. So now I want to consider a somewhat more general distribution. The individual steps, suppose I make those individual steps not precisely plus or minus 1, but I allow it to be drawn from some uniform distribution, right, in the spirit of this generalization here. So it tells you that it doesn't have to be some very restricted sum of variables which are all the same, and nothing like that. It's all these x1, x2, so on can be completely independent. They can be drawn from different distribution. So here what I want to do is draw these individual steps from a uniform distribution in the interval -1 to +1, and let's visualize them, right? So if you want to pause the video here and write your own code to generate a few sample random walks of this kind and visualize them, please feel free to do so. It is easy to do because I have already given you the code for the case where you have plus or -1 type of motion. Some small tweaks to it will allow you to write down the code for this. So you are strongly encouraged to pause the video and work this out for yourself. I have also shown you, the next couple of exercises which are coming your way. If you want to do all of them and only then continue, that's also fine. So here's my solution. So like before, I start my array with just one element, and that element is 0. And then I will use this AppenTo and also the do command. So AppenTo an minus 1 plus 1 minus 2 times RandomReal of RandomReal, right? So what does this 1 minus 2 RandomReal do? So RandomReal will give me a uniform distribution, a random variable with a uniform distribution in the interval 0 to 1. So if I just do this 1 minus 2 times this, it will just stretch out this distribution to give me numbers between -1 and +1. That's all that's going on. And then I will allow n to go from 2 all the way up to 500. And that's it. Basically, I keep on adding this, and that will generate for me a random walk with this distribution. And then I will go ahead and do a list plot. So if I do it once, it looks like this. If I do it a second time, it looks like this. So now you see that it's a little more smooth than before, right? Earlier we got very, very jagged motion because every step was of the same size, right? It could only vary in terms of whether you went right or to the left, but now there is also variation in terms of the size of the length at each point. So you can play with this. You can generate a large number of these and keep on visualizing them, right? I mean, these kinds of things are also done in the context of polymers. You can think of these individual steps as monomers, and you're creating a polymer of a certain size, where the number of monomers is given to you, and you can ask what is the typical distance between the origin or the starting point of your polymer and the end point, and typically it will go as square root n, right? We have seen that. Now the question is that true also for an arbitrary distribution of these individual random variables involved? And so the answer is yes, but let's verify that, and that has to do with the connection to the central limit theorem will become clear in a moment. So in order to do this, what do? I will make a table of this random walks, right? So like I did before, I will generate not just this AppenTo. I will abandon this approach and instead simply generate a table of these random numbers, which are just 1 minus 2 times random real, and n of these, and then sum them. That's completely identical to doing this, and this total is really the sum. You see, it's like this S. So there is indeed a sum involved here, and when you have the sum of a large number of random variables, underlying this is the central limit theorem, and that's where the generality of these results actually come from the central limit theorem. So I'm going to consider 10,000 such samples and then square this stuff and take its mean, right? Mean of m squared, and my claim is that this is going to be linear in n, and I need to find out the alpha corresponding to this. And is there a way to argue for this analytically? So I'm claiming that in this case alpha is 1/3, and I will tell you in a moment why this is the case. Has it started doing it? There you go. Indeed, it's perfectly linear. So the graph agrees excellently with the numerical data of the random walks, and the slope is also 1/3. Why is the slope 1/3? Why is alpha equal to 1/3? And so in order to see this, we have to go back to the central limit theorem, which tells you that sigma squared for the distribution of your sum is given by the sum of all these sigma squared. And if you just compute the variance of the uniform distribution from -1 to 1, how would you do this? You'll have to do integral of x squared, right, times a constant dx, and then x squared will become x cubed by 3, and then if you do the integral carefully and take the limits from -1 to +1, you can check that you will get a 1 over 3, right? The slope of 1 over 3 comes simply from doing the integration right and using this statement of the central limit theorem, right? So that's what is the third part of this exercise. Analytically compute alpha, check by explicit plotting if your numerical data support this expectation. Indeed, it does that. What would be the distribution of the final position you would expect in this case, right? So distribution is also given to us by the central limit theorem. It tells you not only that the mean of this sum is going to be the sum of these means and variance is going to be the sum of the variances, but in fact it tells you more. That's where the power of the central limit theorem comes from, right? It doesn't matter what the random variables, individual random variables, what distributions they come from. If you add a large number of them together, the sum is going to become a Gaussian, right? That's the beauty and power of this central limit theorem. So what I do is I choose n max to be 1000, then I will choose my bin size appropriately. You can play with this, and then I create a histogram of this table of 1 minus 2 random real n max, and then I have also totaled this here. So it's a sum. I have created a large number of these random random variables and created the sum and lots of sums, and I'm histogramming them all together. This is the code. You should look at the code for a moment after you have tried it yourself, right? And then convince yourself. I'm operating this histogram in PDF mode, right? This is something that you have to be careful about. Look up the documentation. You can operate it in other modes as well. So there's a density P and so on. This is the probability distribution function mode. So if I run this, then I will make a comparison between this numerically histogrammed data with the analytical expectation, which from the central limit theorem, which tells me that it's a Gaussian whose variance comes in here, right? It's 1 over square root of 2 pi sigma, and the sigma in this case is just n max by 3, right? Where is that coming from? It comes from the fact that so 2 n max by 3, sorry, so n max by 3 is the variance, right? How do you get that? You get it from this 1 by 3, which comes in exactly from here, right? So it's n times 1 by 3. So that's what is called n max here. So I'm just plugging in the result which we already got from the integration. And now let's check this, and I'm allowing my x to go from minus 5 times square root of n max times to 5 times square root of n max. Let's see what it looks like. There we go. So we see that indeed there is an excellent agreement between the expectation from the central limit theorem and our directly numerically generated data, right? And then the final thing here is to play with other kinds of distributions, right? So now you are free to check the generality of the central limit theorem. You don't have to restrict yourself to uniform distribution. You can generate other kinds of distributions and see how large your number of variables, random variables, has to be before it begins to respect the central limit theorem. So try out crazy distributions like exponentially falling distribution, or some other kind of distribution, and see that the sum is still going to give you a Gaussian. So I have here one another variation of this, which is to choose a normal distribution, right? I have basically the same kind of thing, but now AppenTo, instead of just doing RandomReal, I have RandomVariate of normal distribution, and everything else is the same as before. So this is just to see that you get a different kind of plots. They look slightly different, but they're also random walk, so it's going to give you, every time you try it out, it's going to look different. But by and large, you can see that the distance between the origin and the last point will go as square root of the total number. It's also not evident from here, but for that we will do the next test. And then I have basically used the same code as before, except that now I have a random variate of normal distribution where I had is 1 minus 2 times random real, and then I will show make this show both this list plot and the plot together on the same graph. There you go. And so once again the data sit on top of each other, so there is excellent agreement of this data as well, and there's a with this expectation from the central limit theorem. So once again you can go ahead, and so I claim that this part is not going to change, right, because it's still okay. So the only thing that has changed is sigma squared now is just n max. It's not, there is no 1/3 here, so that part has changed, but otherwise it's still a Gaussian distribution, and you can check this. Indeed, the two of them agree very well, right? So this discussion was to give you a quick flavor, or to just state the central limit theorem and give you an idea of how to play with random variables and develop a feeling for this theorem. So there is one more small topic which I want to cover in this context, and so the question is, why is diffusive motion so common, right? One way of thinking about this is in terms of the central limit theorem, and another is the following argument. So the law of diffusive scaling is very, very general, right? And it comes about not only in the context of this random walker, but in whatever dimension you are in, it holds. So why does it hold in arbitrary dimension? So this argument I find is actually quite neat to see why this comes about. So consider a random walk in which each of the steps is a vector. Don't think of it as going to the right or to the left. All directions are completely open, let's say. So let's call these vectors as r1, r2, r3 all the way up to rn. Since every direction is assumed to be equally likely, so the average of each of these vectors has to be 0, right? So given it's simply a sort of directional average, you can think of this as, it doesn't matter what the magnitude of this individual vector typically is, but since every direction is equally likely, the average of each of these vectors is 0. It's a vectorial average in some sense, right? So we can take the typical length of each vector to be a, and so this information can be compactly put into this equation. Average of rj dot rj, the dot product of a vector with itself, is a measure of its the square of its distance, or of its size, and so the typical length we will take it to be a squared. So now think about this vectorial displacement. So if you add n such vectors, r1 plus r2 plus r3 all the way up to rn, so the average of this net displacement is of course 0, because the average of each of these vectors is individually 0. Therefore the sum of all of this is also 0, right? But if you consider the average of the square of the net displacement, in other words, if you take the dot product of this sum with itself, right? So this is a little bit like the central limit theorem, but here this is much less abstract, right? This is very simple set of ideas involved, and just using the idea, the notion of vectors. So if you do r dot r, so you will see that there are all these terms which involve vectors multiplying with themselves, r1 dot r1, r2 dot r2, so on, and then you have all these cross terms. These cross terms is where now comes the key argument, right? So basically you argue that this random walk is completely memory free. So every step simply doesn't care about what any other step is doing. At a given point you go to the next point, and then you have a fresh decision to make, and you take any direction, and within the distribution the size of the step is completely open to you, right? And therefore you can say the average of this ri dot rj is actually nothing but the average of ri times the average of rj. So this is the key point. If these two are completely independent, that means that the average of the product is equal to the product of the averages, and each of these averages is separately 0, because every direction is completely equivalent, and therefore the average of ri dot rj is equal to 0. So they are completely uncorrelated, and so that's why although you have a large number of sums, there is these n terms, but there is also n times n minus 1 2 by 2 other terms in this summation here. All of that will just simply go to 0, and then finally you are left with simply average of r dot r is just equal to these sums. Each of these typically has the same length, a squared, a squared, a squared. They all add up, and then you get n times a squared, right? So this is a very nice, beautiful argument, which immediately gives you the statement of the diffusive motion. Basically, what it tells you is that if you take n steps, you are typically only going as square root of n, right? If you will have to take the square root of this overall stuff, then you will have square root of n times a. You have taken n steps, but you have only moved square root of n times each individual length step involved, right? So that's nothing but the statement of the diffusive motion coming from some very, very simple direct arguments. All right, thank you.